Absorption of light. So we said that in the ultraviolet and in the visible region, when a molecule absorbs light, it will cause excitation of electrons. And normally because the molecule or the matter will absorb light, it means it will absorb some energy. So that means that the energy of the molecule will increase. When the light is absorbed by the analyte or the substance in question or the substance that is will interact with the light, the radiance, which is defined as the energy per second per unit area of light of light beam, and we usually give it the symbol P, will decrease. That means when you have your sample and the sample here in we put the sample in the cuvette as we did in the spectrophotometer, and usually we have a light source. This light source is a polychromatic source. It has all the light beams from the ultraviolet and the visible region, and this light goes through a wavelength selector, or what we call monochromator, because as you know, when you use the spectrophotometer, you used to measure the absorbance at a certain wavelength. So the light passes through a monochromator that select a certain wavelengths. And then this light has certain irradiance, which is P naught. So the irradiance now is P naught. As it passes through the sample, the sample will absorb some of this light. So the irradiance that emerges out from the sample, which is given the letter P, will now have less value. So the irradiance will be less because some of the energy has been absorbed or some of the light has been absorbed. And this passes through a light detector, and the light detector will measure how much light has been absorbed. So we usually measure the amount of light that has been absorbed by measuring the transmittance. So the transmittance is the fraction of the original light that passes through the sample, which equals P over P naught. So this is the fraction of light that already passed through the sample or has been absorbed by the sample, which means the percentage transmitted will equal P over P naught times 100. So this is the percentage transmittance. Peirce-Lambert law, and you all are familiar with Peirce-Lambert law, is the law that correlate the absorbance or the transmittance with the concentration of your sample. So absorbance equals epsilon, which is the molar extension coefficient, and this is a constant value, and this is constant for the certain chromophore or the certain colored solution that we are using, or the colored complex. This is constant for the certain complex, and it differs between one complex and another, times the path length, which is B, which is the length of the path of the sample. This is mostly 1 centimeter, like the one you used in the lab as well, times the concentration of your analyte. And the relation between the absorbance and the transmittance is seen in this equation here. So absorbance equals minus log T. So the absorbance is log P naught over P. And this equals epsilon times P times B times C. In the spectrophotometer, the result that you see on your screen is the absorbance. So basically what happens is that the spectrophotometer will measure the difference between the irradiance of the light irradiated and the light that comes out from the sample solution. And this is expressed as the absorbance. We don't see the transmittance, but you see the absorbance as your value. This is because Peirce-Lambert law is a relation between the absorbance and the concentration. So absorbance is proportional to the concentration of the light absorbing molecule in the sample. Um, the part of the molecule that is responsible for the absorption of light is usually called chromophore. So the word chromophore comes from the word colorful. So this is why we call it chromophore, because now we are talking about light. So we are talking about mostly visible light. So all the substances that absorb light must have a color. Chromophores are functional group that cause compounds to be colored. And usually chromophores have electrons that can be excited when they absorb light, because we know that absorption of light in the ultraviolet and visible region will cause excitation of electrons. These are mostly unsaturated carbon-carbon bonds or systems that have many unsaturated bonds or transition metal ions. Like the complexes we formed in the lab between iron and 1,10-phenolphthalein. This is a complex between 1,10-phenolphthalein and one of the transition metal ions, which is iron. Or in the first lab when we did the first experiment where a complex has been formed between copper and ethylene diamine. Sometimes a very small change in the structure may cause a change in the chromophore in the substance. An example of that is phenolphthalein. So we all are familiar with phenolphthalein, that is pH dependent, and phenolphthalein has been used as an indicator in acid-base titration. Phenolphthalein and pH less than 8 is colorless because this is the structure of phenolphthalein and it doesn't show any color. But once the pH goes high or the system becomes alkaline with pH higher than 8 or 8.1, the color change from colorless into pink. This is why when you do titration, acid-base titration, and when you use phenolphthalein, if you have acidic solution and you're titrating with alkaline solution, the endpoint is the first appearance of the pink color. This is because there is a change here in the structure at pH higher than 8, which causes the creation of a chromophore. Beer's law is the law that we use for measure the concentration of substances in relation to their absorbance of light. So the higher the concentration of the sample, the higher the absorbance of the absorbance of the substance or of that colored complex. However, it has a very wide application in analytical chemistry, but it's still a very limiting law. It's limiting because it's only applied to monochromatic light, so you can't use it with polychromatic light. So you have to use a certain, and have to do all the measurement at a certain wavelengths. Also, it's only applicable at very low concentration. So normally we have to dilute our samples so many times to get to concentration as low as possible in order to be able to use the Beer's law. At higher concentrations, the law will not be applicable because when you do your calibration curve for concentration against the absorbance, you usually get the straight line. So at certain concentration, if you get to a much higher concentration, the curve will not anymore be a straight line, but it will start to be curved like this. So the Beer's-Lambert law is not applied at higher concentration. Also, if your substance undergo any chemical change with a change in the concentration, you cannot use Beer's law. For example, you know that weak acids are concentration dependent. So the higher the concentration of the acid, the more the dissociation of the acid, which means that the concentration of the acid remaining will decrease, although you increase the total concentration from the beginning. That means you cannot apply the Beer's law in this case. So anything that will show a difference in the equilibrium with the change in the concentration cannot be used with Beer's law.